Okay, so we are on lecture 21, and we're going to start talking about graphs. So we haven't really talked about general representation of connected structures before. That's essentially what a graph is. We have talked about trees. We talked about binary search trees, and we talked about connecting those things up with sort of a left pointer and a right pointer kind of thing. Undirected graphs are much more flexible and can represent a far larger range of problems. So we're going to be spending quite a few lectures on graphs in general, probably about 4 or 5 different lectures. And that's even going to continue even beyond graphs. So this is a really powerful data structure, and one in which you can solve a very large array of problems. And it's been around for quite a long time. So it is heavily, heavily studied. Um, quick reminders about the week. So we have our homework 5 and quiz 5 tonight. Now, I did just sort of modify our late policy. I kind of looked at what the four-year universities do. It is sometimes the case that you're given a pool of your free, they call them slip days. So slip days are just free days you can apply if you need an extra day for a major homework. So I've added 3 slip days for everybody in the class. And so if you don't get an assignment in when you do finally turn it in on time, just tell me how many of your 3 slip days you want to apply to that particular assignment. So we'll only give you 3. And then once those are gone, or when you don't use those, we'll start applying our usual 10% per day late policy. Okay. So I'm going to keep it kind of loose. There's a lot of rules that different universities apply, like you can't use more than 1 slip day per assignment, etc. I'm just going to keep it open and we'll see how it goes. I've never really done this before, and I would not do it with my beginning classes. So I'm only going to sort of enable it for advanced students, or upper class students, if you will, because you kind of know where you need the extra help and when you need it. So use those 3 days sparingly, especially if you need them on your homework 5, and we'll go from there. Now, quiz 5, I'm not applying that to, so it's important for you to get your quiz 5 in tonight. If you have not done that, I got to give you a 0 for that. So please do jump on that first before you do anything else, and then you can kind of consider your strategy for your homework. So let me see if anybody has any questions with that so far, because that's kind of a major change. Okay. All right. Well, let me know if you have any concerns or questions. Just email me in Canvas and we can kind of go over that. Hopefully, it gives you some extra flexibility on stuff. So for Friday, we'll have a lab 21, which is printing friends of friends in a graph. We'll go through that. You can see that on Canvas. There's some good help there. That is due on Friday. Haven't figured out what my Thursday lab is going to be yet. So stay tuned. I'll try to kind of pull something together that's not too overwhelming. In 2 weeks, we have a homework 6, like usual. This is a choose your own adventure homework. So we'll dive into this in a second. There are 4 different pathways you can take, depending on which story problem is more interesting to you. They all revolve around the same concept of something called connected components. So really, even though they're slightly different, they will all utilize a lot of the same code that we're going to start introducing to you today. So by the time you get 2 weeks out, you should be really familiar with the code that we're going to start working with, and you should be able to apply it to solve story problems. This is really one of the skills we want to take away from this course, is understanding how to apply very well-known data structures and algorithms to story problems. So this will be kind of one of your first chances to think broadly about how you might attack a problem. So, and I'll guide you through it step by step. We'll go through those things briefly here. And then we'll have our usual quiz 6, and there'll be some Quizlets there for that, because there's lots of terminology we're going to start getting introduced to here. And our last data drop is coming up. I think everybody's doing okay, but just heads up, Friday, November 21st, I think, is the last data drop of the W, if you feel like you need to do a reset. And I always tell everybody, if for any reason you need to do that, you're always welcome to come back and take it again. As you know, we only offer this once a year, so that's a long time to wait, but it's there if you need to pull that trigger. Okay. Now, Next Tuesday, no lecture. I'll remind you again on Thursday, but it's Veterans Day this year. And so there is no class on that Tuesday. I'm still trying to figure out how to make up the loss of that day in terms of our schedule. So bear with me while I sort that stuff out. Looking ahead, of course, no lecture on the last Thursday and Friday of November. That's our Thanksgiving weekend. So you won't have a lecture there either. And then the last lecture before final exams is about December 11th, I believe. And then we have a week of final exams after that. I'll double check that date. Somehow that seems like that's a little earlier than it should be. Yeah, okay. And then the 16th, right, is our final exam on Tuesday. So we're kind of rounding the corner toward the end here. It's not that far out. So it's good to just kind of keep in mind what we got coming. Okay. So those are kind of the high level things. So this homework 6, we're just going to take a quick peek at these so you kind of get a sense of the kind of problems you should be able to solve in about 2 weeks. So there's 4 different homeworks here called electrical grid, virus alert, book of stones, which is kind of a silly one, and then some Star Wars alliances. So you can kind of pick the one that seems the most fun to you. They are mostly roughly about as difficult as any of the others, just with slight different twists to them. So most of us will be working with the same code base, maybe just trying to answer a slightly different question given the data sets that you're going to be given. Okay, so let's take a look at these real quick, these 4 options. So electrical grid. So here's one. A hurricane has ravaged a small island and caused widespread damage to its electrical grid. Wires between many of its 1,000 electrical poles across the island have been torn down by trees and wind, cutting off power to the residents. The power authority would like to go out and provide power to subgroups that have at least 10 poles still connected. So they have these generators, they can go out and hook them up as long as you've got about 10 of these poles with wires connecting them. So these are one of the fundamental questions we ask about graph structures is like, if I have a whole bunch of poles, some with connections and some not, how do I find islands or what we call components that are sort of connected to each other in some way? Okay. So searching through 1,000 poles to figure out what are those little islands of connectivity is a very important algorithm. And that is one that we're going to study over the next 2 weeks. So this electrical grid problem for homework 6 is just that. You have a huge pile of poles. You have to go find all the islands, and you got to figure out which ones have at least 10 telephone poles connected. And you'll get a better sense of this as we look at some of the graph structures today. So you're going to do that, and you're going to print out what are the IDs of all the poles. Like here are 10 poles, here are 15 poles, here are 100 poles. There's going to need to be at least 10 poles in your groups. Some groups will have 3 poles or 2 poles or 1 pole. You're not going to be really interested in those particular groups. Okay, so that's our option number 1 for electrical grid analysis. Okay. Virus alert. This is probably one of the more fascinating but challenging ones, but it very much mirrors what kind of was going on with COVID, right? So I don't really know exactly how Google did this, but here's our story. Google recently launched an opt-in exposure notification feature for all of its Android phones to notify people of their exposure to someone with a virus, okay? So some of us will remember that. Google is going to assign a unique ID in random order to everyone with a phone from 0 up to, a really, really huge number there. Okay. So everybody gets a unique ID for their phone. Okay. So in that sense, you're kind of like a telephone pole, right? Thinking of our previous problem. So all of us are those telephone poles. Google is going to constantly record when 2 people come within a certain proximity of each other, just so it has some history of their connectivity. So if you and I come within 2 feet, boom, we're connected. So that's like a line between 2 telephone poles, regardless of whether or not one of us has the virus. Okay. So we're going to notify Google of our proximity. It's going to write down that connection and remember it. And then at some later time, we need to be able to go back to all of that pile of data when somebody is exposed to the virus and say, uh-oh, who are all the people in this island of connectivity who could have been exposed. So we're going to treat the virus exposure like an electrical signal that just travels through all of the people that we kind of met within a certain amount of time. Okay. So it's very similar to the electrical problem, but we're going to have just a few more constraints. Like, well, if you got exposed to me before I got sick, then that's okay, right? You're going to be fine. So there's a little more data in that one. You might find that to be interesting, but maybe a little more challenging. Okay. Book of Stones is kind of a silly fantasy story. There are a bunch of stones crossing a river in random patterns, right? It's not just a straight line. They're kind of all over the place. And ideally, you're trying to get from stone 0 across the river to stone 99. But like most stones in a real river, they're spread out all over the place, and you may or may not be able to reach the next stone. And you might find yourself stranded where you get to a place in the river where you can't get to another stone and you may have to backtrack. So we're not really looking for a pathway per se. We just want to know if there are a bunch of stones all within reach of each other, yes or no. And that collection of stones would be like a component or an island of connected stones. So our connections here, instead of the electrical wires between telephone poles, are the stones that are close enough to each other that we can step from stone to stone. So in this case, the relationship that is the edge or maybe the connection between stones is the fact that I can reach it. Okay. So we'll have some data that would help you figure out which stones are connected to other stones, and you will need to figure out if you can cross the river or not. Okay. So that is called our Book of Stones. Okay. And the last one is kind of a Star Wars, good versus evil kind of scenario. So we have Yoda is represented as a telephone pole. We'll call Yoda node number 1, and we'll call the evil emperor node 0. And these are competing to convert the largest independent group of, friends to their respective light or dark sides, right? So all of the nodes in this graph, or think of it as the other telephone poles if you like, we want to figure out, where is a group of undecided voters? You can think of it that way. So, which is the biggest group that's all connected where we can say, hey, we would like you to move to the dark side or you to move to the light side. So in this case, we're looking for connected telephone poles in the largest group, and then we're going to try to recruit them over basically and say, hey, this is my target audience here. Okay. So we want to go through all the nodes, see which ones are already aligned with or connected to node 0 or node 1. Those are already kind of won over, right? Those are either the dark ones or the light ones, right? On the Yoda side or the evil emperor side. So we don't care about those. We're trying to figure out the largest independent group. Okay. And once we identify that, we can list the nodes that are inside of that. Okay, so once again, we're really analyzing connections, looking for islands of connectivity in the middle of all of these messy connections. Okay. And they're so big and so complicated, we couldn't just draw a graph and try to figure it out on the screen. We can only really do it with a computer program. Okay. So those are our 4 options, and you'll have been given the code to do all of this. So it'll just be about learning how to apply that code to solve the particular problem. So you're not going to be writing a lot of code for this, but you will be copying a lot of code from our practice problems. So what we're going to do over the next 3, 4 lectures is introduce you to a fairly large body of code that is a solved problem. And it'll be important for you to understand the code and understand how to read it and apply it to the problems that you choose for homework 6. Okay. Any questions on those so far? All right. So hopefully once we get there, the Canvas assignment for homework 6 will provide, some additional help for you. I will be dressing those up a little bit, so there's a little more help in Canvas. I think it's pretty minimal right now, but there's still some good information in the slides that are coming. Okay, so for today, we're going to kind of start off and we're going to talk about graphs. We're going to introduce ourselves to the vocabulary of graphs. And graphs could really be anything where there's a connection or a node. So the dots here, there are cities maybe, or stops on a subway. We could think of that, about those as nodes in a graph. And when two nodes are connected via some subway section, we say they have an edge. Okay, so we could take a map like that and kind of boil it down into something more simplified down here. I notice that my graph on the bottom here has sort of two islands or two components. We consider this to be one graph, but it's got a group connected on one side and another group connected on the other side. Now, visually, we can look at that and it's like kind of obvious because those things are kind of laid out nicely. But in the real world, it's much more difficult or a lot more difficult to do that visually. So when our edges do not have any directions, like two-way streets, we call that an undirected graph. So every edge that connects two vertices is essentially undirected. Now we could, like with Google Maps, assign a weight to each of the edges that represents something like distance, or if it's an electrical system, it could be resistance, or if it's a transaction between banks, it could be a cost for the transaction or a transfer of funds. So our undirected graphs can be weighted or unweighted. So in this graph we see below, we don't see any numbers on the edges, so that's an unweighted graph. We're not really representing a cost to that. We could also have directed graphs that are more like one-way streets, like we have maybe in downtown San Francisco. It's like if you want to get from A to B, you could only get there one way. And if you've ever been stuck driving in a city with a lot of one-way streets, it can be pretty infuriating because you can't find a way to get back to where you were. And that is very true about graphs as well. So if you have a directed graph, you may not be able to get back to where you were. Those are more challenging graphs to analyze, and that will be kind of phase two of our big conversation on graphs. So we'll start out with undirected, and once we get that one handled with homework 6, we'll switch on over to directed graphs and tackle the harder problems on those things, okay? So in all of these graphs, we have vertices and we have this thing called vertex degree. So a vertex and a node are pretty interchangeable. So we'll look at the code for that here shortly. But the degree is how many neighbors you have. So this vertex 3 is a degree 2 vertex. It's got two neighbors, number 1 and number 4, right? Vertex 2 has a degree 3, all right? So I think everybody can kind of see that pretty clearly. So that's our degree. Our edges, again, are the connections between the vertices. And adjacencies are pretty similar to degree. But what they really are referring to are the specific adjacencies. So in our lab today, when I say, hey, who are all the friends of vertex 2? Well, first off, who are the friends of vertex 2? It would be 4, 1, and 0. So you can see how a social graph like Facebook or something like that, or Instagram or anything, LinkedIn, these things are essentially graph structures where relationships between people can be represented that way. So adjacencies are kind of like, who are your first level friends in a social graph? Okay. Friends of friends is something else. So if I say, who are all my friends of friends? Well, friends of friends would include 3. And if the graph was bigger, it could, reach out to other places, right? So your lab today is about finding friends of friends, which is a little more indirect, but not that hard. And here adjacencies are just our direct friends, okay? So connected components, again, that's our little island, okay? So if these were bridges and you couldn't get off the island, well, that makes that a little clearer, right? A component is an island where there's no way to really escape the island, okay? And so even though this is all one graph, it kind of has two islands or two connected components. Now a graph with no edges, if this had no edges, it had just 7 vertices, 0, 1 through 6, then you would have 7 islands, right? So without the connectivity, every vertex becomes an island to itself or a component to itself, okay? That's sort of one of our definitions. Cycles we'll talk about in time. So can I go around the outside or can I get from one back to itself? That would be a cycle. And undirected graphs have lots of cycles. Almost everything's a cycle, obviously, in an undirected graph. If it's a directed graph like downtown San Francisco with one-way streets, maybe it's not possible to get back to where you started from. So some graphs have cycles and other graphs maybe have no cycles. Okay, so finding cycles in a graph is a really important algorithm. How do we figure out whether a particular graph has cycles or not? And we'll study that one for sure. And then the last kind of major thing is paths. If I am here and I want to get to over here, from LA to New York, is there a path? And what is the shortest path? If every edge has a value, what are the shortest paths I can find from one place to another? And that's a really important problem. Okay. Obviously, we do it with Google Maps or any kind of interactive maps program all the time. And it happens in real time and it happens, depending on how much traffic there is. So, but we'll be studying the fundamental algorithm for how we actually solve that. Now, all of these questions are going to take us back to our recursive roots. And if you remember in our binary search tree, we talked about depth first search or breadth first search. These are going to come back to us. We're going to need to do more and more of this recursion. So this terminology we'll review again, and we'll see it used in a slightly different code base, but it's still going to be about exploring all possible avenues through a recursive approach. Okay. So, and pointers are going to be an important part of that in this particular case. Okay. So we'll be seeing a lot of that coming up. So those are kind of our primary concepts. Let's kind of dive into some examples of graphs here. Now notice here I've represented our nodes with a value that is a letter. Okay. So our nodes could have a word or a letter or a number or a last name. And usually out in the world, that's kind of what they represent. Maybe it's Los Angeles or San Francisco. But when we study the graph, there's no particular route to it, right? So it's not like a tree where we say we always start from one place. We could choose any one of these nodes to be our route and then begin our journey. So that's one aspect of graphs. And there's no particular way we got to go. Like, so we could start L and go to E and F and then realize, oh, I've already seen L, so I'll go to G now. Or I could go from L to E and then go to D. There's no rule about how you do that. It's just how do we want to do it in our code, okay? Now, at some point, again, in these undirected graphs, a lot of loops, which is helpful, right? We can always get back to where we started, okay? And our edges don't really have any constraints. We should be able to travel in either direction at any time. So either our nodes are connected or they're not, okay? And in terms of our language, if I say H is connected to A, that means I can get to A somehow from H, whether it's this way or this way. I could get from H to A in probably a lot of different ways. So sometimes we want to find just one way to get there. Sometimes we want to find all the ways to get there. Okay. So those connections can be indirect. So we would consider this to be a graph structure. Sometimes people call it a network model, but it's pretty darn cool. And if you can imagine, people as telephone poles or social media or bank account transactions, the list goes on and on and on to all the problems we could possibly solve. And you can kind of see where the weight could be anything. It could be, hey, am I going up a hill, to get from A to B? Okay, or is there some resistance that I have to deal with in an electrical network? Or if it's a pipeline where we travel water or oil between cities or countries, how wide is that pipeline? What's the velocity that you can travel through on that? So lots and lots of ways we can use weights to sort of represent some real world situation. Okay, super powerful representation. Okay, now directed graphs we'll get to in a couple weeks, but here's an example of a directed graph. So here, a little more fun, kind of like a maze, we could start anywhere we want, but we might be pretty limited. If I start at M, I can't go anywhere, right? If I start at K, I can go to M. That's about it, right? but that's just the game we play when we have a graph with directed edges. So they can be cyclic in nature, but not always. There could be loops in there, but it's not a guarantee. And it's not the case that every connection is bidirectional. Okay. So sometimes we would have bidirectional and sometimes we would not. Okay. And I think this particular graph is all one directional edges. Okay. And they could potentially be weighted as well. Okay. So if I was going to have a back and forth between Z and H, I would represent that in a directed graph with two separate edges. Okay. So unlike our previous graph that was undirected, here we actually have to express that extra edge to sort of show that, or at least graphically we would show it that way here on this picture. Okay. So different applications, of course, subway system, right? You know, some things are multi-directional, some are not. They might be one way. Protein interaction networks are very often represented this way. So modeling stuff like this is incredibly, helpful for medical research. Clickstream maps of science references. So if you want to know which papers are based on which other papers and which other papers are referenced, or who's the most referenced, researcher out in the world, there's a lot of ways to track that stuff that's out there. And then, of course, social media networks can be represented that way as well. And there's a lot of analysis, obviously, that companies like Facebook do for determining virality and connectedness and interest level and things like that. So a lot of the algorithms that, we think about or talk about or that get a lot of good or bad press sort of derive from analyzing these graphical networks and then doing something like, oh, you're friends with these people and they like this product, maybe we'll promote that product to you as well. Okay. Um, so whole lots of stuff, including the internet, right? Internet connectivity. And one of the things we'll talk about is, sort of malicious attacks on the internet. If I could find a node in that internet there that was highly connected, I could take down that one node and disrupt a large amount of the global internet traffic. So the design of the network graph itself and the ability or, unfortunate ability for people to attack and, dismantle a particular node can have, profound effects on everybody. I think we've probably felt something like that recently, although I don't think it was really an attack so much as just a failure. So let's kind of dive into how we're going to analyze these things. So we'll say vertex or node, right? So there is a particular vertex or a node, and we'll say that it's adjacent to Q, right? Any vertex that is directly adjacent to vertex Q would be an adjacent vertex. Okay. So I don't know why I said Q here. I don't even see a Q on there. So sorry about that. Probably should say adjacent to A, right? Not Q. So A here is adjacent to J, N, and B. Okay. So that's a little bit of a oops. And then we have our single undirected connection between these two particular vertices. Okay. So we can kind of see what those are. Okay. A pathway would be just a connection of these edges. So A, N, Z, H, right? Including the edges between those. And the length of that path would, of course, be the number of edges along that path. A cycle would be something that sort of kind of wraps around and comes back on itself. So you start from one vertex and you have to be able to get back to that same vertex in some way. As we were saying, for undirected graphs, cycles are pretty darn common. You can usually get around pretty easily. You said the degree of a vertex is how many direct friends or neighbors it has. We call those adjacencies. So the degree of F here would be 2, the degree of C would be 3, and so on. Okay. And the connected component here, if I were to say how many connected components in this graph, if we looked at it for just a second, we can kind of find the islands with our eyes and see that there are 2 connected components in that graph. And if we wanted to, we could name off the individual nodes that are part of each of those connected components. Okay. So visually, we can kind of find that out reasonably well. Okay, so there's one island, and there's our other island. Okay. And we will definitely look at algorithms for finding those answers. Okay, and that's for sure what we're going to be doing in homework 6 with our different story problems. Okay. Okay. So now how do we represent these things in memory? So there are a number of different ways. And the primary way that we're going to use is something called an adjacency list. But we're going to take you through all three of the major ways of representing graph structures in memory. So the graph visually on the left there has these vertices A through J. And each vertex, we can list its friends, if you will, its direct friends, and we'll call those its adjacencies. So A has J and N, B has K and C has B, L, and D, and so on. Now notice there's some redundancy to our data structure. So if you look at C, it's listed in a number of places. Not only do we list C's friends over here, but you can see that C is also being listed by the same ones that C lists. So if C is pointing at B, then B should be pointing at C, right? And L should be pointing at C. So there's some redundancy in this approach, but what it gives us is very immediate access to all of the information we want to know about a particular vertex, okay? And if you think of this as an array, this is position 0, 1, 2, 3, etc., right? 4, okay? So what we're thinking about doing here is organizing adjacencies by position in an array, okay? So remember that when we get to our code here in a few minutes, that's going to give you a little bit of an intuition about where we're going, okay? So if I want to know everything about A, I would go to position 0. If I wanted to know everything about E, I would go to position 4 in an array, okay? So we sort of implicitly kind of assume that that reference is going to be oriented, along the lines of our array positions, okay? So we'll come back to that, but you can kind of see the redundancy there, okay? I think I picked on C, but this is sort of illustrating that for A, okay? All right, so common graph questions we might ask. I think we touched on some of these, but is there a path between two vertices? Okay, we can visually see it, but can we do it in code? That's going to be a fun one. What is the shortest path between two vertices? That's a really good one. That's a very useful question. Is there any cycle in a graph? So if I was telling you, hey, we're going to build a rocket, it's going to go to Mars, and we have about 10,000 things that we have to do, some that depend on other things being done first, we really don't want any of those dependencies to be cyclical, right? So if I have a graph of all of the things that need to be done and what order they need to be done, we really hope that graph has no cycles in it, because that means that we can't get to Mars. We can't finish a project because it depends on something that depends on us. So finding any cycle in a graph is sometimes a very useful question to be answered, because it means, uh-oh, we got a bad graph, right? It should be more like a tree, but it's acting maybe like a cyclical graph. So finding cycles is a really important thing. And also, is there a cycle that uses every edge only one time? So if you are a delivery person, like working for Amazon, and you got to go to every house in a particular neighborhood, what is the best way that you can do that in a neighborhood so you're not driving up and down the same street a bunch of times? That is what's officially called an Euler tour. It's a not always a solvable problem. So not every graph can allow us to hit every house in a neighborhood and visit every street only once. Some graphs will let us do that. So we will study that problem and study the idea of a Euler tour. Another more famous one, sometimes called the traveling salesperson or Hamilton tour, is similar, but much harder to solve. In fact, it's not really efficiently solvable. We can only sort of try to do it as fast as we can. But is there a cycle that uses each vertex only once? Okay. So can we kind of visit and deliver the packages without traveling past a house twice? Okay, that would be the analogy there. So that is an even harder problem to solve. Can we connect? Is there a way to connect all vertices, right? What is the cheapest way to wire all the homes in the neighborhood with electricity by using the least amount of electrical wire? That's another problem. We call that a minimum spanning tree. Okay, so that's a fun one to solve. And is there a single edge that, if removed, will break the graph into two separate components? This is what we call a min cut. Believe it or not, this problem goes all the way back to World War II, when train lines represented graph structures, and supplying resources to the warring sides of the different countries was all about sort of cutting supply lines. So if you can find the edge that cuts off the most, that separates things into two separate components, that means you've cut off the supply. There's no way from one island to get to the other. Okay, so finding these minimum cuts is another really important question that we would like to be able to solve. And there's more. Cutting, drawing something in a plane with no crossing edges. Do adjacency lists represent the same graph? These are some really fun and somewhat, quite challenging problems. Some are relatively easy to solve. Some are really hard to solve. Okay, and some are there's still research going on to solve some of these problems more efficiently than someone else. Okay. So we'll try to pursue some of these. We certainly won't be able to do all of them. Now, we could draw these graphs in multiple ways. These are the same graph, okay? So, how we lay them out on paper is just, how we visualize them for us humans, computer doesn't really care, about the visual layout. It's really just more for us, okay? So let's see how we're going to represent this. So first off, we're going to simplify by, instead of using letters or words or last names, we're just going to assign integers. So if there are 6 cities that we want to connect, we're going to give them numbers 0 through 6. And we're never going to add or delete cities, okay? So once we start analyzing a graph, we're going to, for this class, assume that there are no more or less vertices. So if we start out with 6, we're going to always have 6, and there will be no gaps. 0, 1, 2, 3, 4, 5. Those will be our 6 vertices, okay? So in that sense, n here is going to be equal to 6, okay? And for our class, we'll always know n before we begin researching a particular problem, and there will never be a gap, okay? So we could use array positions 0 through 5 to really represent the starting point for any particular vertex. And that's a really useful simplification. We don't have to use pointers if we can find a way to use a simple array, okay? So we're going to use these integer IDs to represent the vertices, and then we'll do something from that point to represent the adjacencies, okay? So our recent homework with symbol tables, we kind of know that we can crunch stuff down into a particular bucket number. So we could always figure out how to go from a symbol into an integer value if we really need to. But for this part of the course, we're going to put the sort of words behind us and just focus on integer values for a while, okay? So, for example, I could say, hey, what's the vertex ID for Chicago? And boom, now I know which vertex is Chicago, right? 0, 1, 2, 3, 4, 5, okay? So we're going to wave our hands at that a little bit, and now we don't have to really worry about those words anymore, okay? Okay, so things we got to be aware of. We won't do this too much, but it is possible for one city to point at itself. That's a little weird, that you can get to a city by following an edge back to itself. It is possible that we could express multiple ways to get between 3 and 4. Okay, now you might think that's not necessary, but maybe there's 3 ways to get between, San Francisco and LA, right? So each of those could have a different weight. So maybe there'll be times where we want multiple paths and other times maybe not so much, okay? So we need to think about how we're going to support that or not support that whenever we sort of build something in code. So let's look at an abstract data type or an interface for this particular idea of a graph, okay? So first off, we need a constructor. So if I say, hey, I want you to create a graph with n things, no connectivity, right? So now we have a bunch of dots floating on the screen, but none of them are connected. That's okay. That's one simple way to start a graph. I could also say, hey, here's an edge list, maybe an array of edges with vertex IDs, and I want you to create a graph that has all those things connected. So that might be another way to do it. And at any time, we might want to connect two existing vertices. Like, hey, add an edge between 0 and 7. Add an edge between 2 and 3. Okay. And we generally think of this as the from vertex to the to vertex if we're working in a directed graph. Okay. But otherwise, we assume that it's going to be bidirectional. Okay. So that's our add edge. Okay. Now, an adjacency we'll dig into. The adjacency is kind of like the underlying structure of an edge. Does it go in two directions or does it go in one direction? And we'll dig into that in code in a minute. So at any point, we might want to know who are all the friends of a particular vertex? Who are all the adjacencies? So get the adjacencies is kind of like saying get a collection somehow of all the vertices that are directly adjacent to vertex V, okay? And V could be any value from 0 to less than n, okay? So that's what we mean by get adjacencies. Now maybe it's a vector, maybe it's an array, maybe it's a linked list, right? It all depends on our implementation, okay? So that's get adjacencies. Edge count, how many edges are in the graph, the whole graph. How many vertices, which is always going to be n, right? That is always going to be n, okay? If I create something with n vertices, that's what's going to happen. And this is just a way to print things out. This is our first practice problem in class today. I think we'll get through to that. And then print edges is something else we could do, okay? We could imagine more interface methods for our abstract data type, but these are pretty much the ones that we're going to need to kind of get up and running, okay? So let's kind of dig into that a little bit and see if we can get into some of our code. Okay. And again, remember that in our directed or undirected graph, for us, an edge is going to create an adjacency for both V1 and V2. So essentially, each edge has to represent two adjacencies. V2 is a friend of V1's and V1 is a friend of V2's in an undirected graph, okay? They're connected in both ways, okay? So we'll see that here shortly, okay? Okay, so let's talk about the data structure in more absolute terms. So we could just do a list of edges. When I started out in graphics in college, I was studying a lot of geometry and I thought, oh, how do I represent a square? Well, a square is made of 4 edges. Okay, well, that seemed like, 4 pairs of things. But I realized pretty quickly that I was sort of listing the same vertex over and over and over again. So we get a lot of vertex duplication if we just decide to represent our graph with edges. And that's not really necessarily a bad thing, unless we have a lot of dense connections. If we have a lot of dense connections and very few vertices, then it's kind of inefficient. But it can work in certain situations, right? So here you can kind of see where 6 has got, we have 6 and 7, right? And then we have, well, we list both of those vertices and we list 6 again in multiple other places, right? So it's a little bit inefficient in that sense. Another one, and this is actually one that's used in a variety of applications, is an adjacency list for matrix. So here we can say, okay, for every crossing point, right? 6 and 7. So if I look at 6, I can kind of see by going across the rows who I'm connected to. True and false, I can always ask the question, is 6 connected to 7? Is 6 connected to 5? And in reality, every one of these on the diagonal should have a true there because, right, 2 is connected to 2, 3 is connected to 3. That's sort of implied there. Okay? But we could use a two-dimensional matrix to represent that. Okay, so that's the other of our choices there. Okay. And in fact, some people would say that's a really good way to go because with graphics cards or, now AI optimized matrix operations for neural nets, we can represent very large matrices, sparse matrices like this, and ask questions by doing matrix math. So for those of you are considering or currently doing stuff in linear algebra or have done that or working in calculus or doing any kind of vector math in physics, this is where you start to go, oh, okay, yeah, I could do some matrix multiplications here and answer some really important questions. And that is absolutely the case if you represent these graphs in a matrix type style like that. Okay. So for example, and I won't dig into this too deeply because it's not a core of our class, but if I were to take, a representation of vertex 1's matrix adjacencies, and then a kind of a binary representation of the fact that I'm 0, 0, 2, 0. I'm interested in the 0 relationship. I can AND those two bit values. I can do a binary AND between this and this, right? So a 1 and a 0 is a 0. A 1 and a 0 is 0. A 1 and a 1 is a 1, right? So if ANDing these things gives me back the answer, gives me back essentially what I'm looking for, then I know there's a connectivity there. So we could scale that up to a huge, huge level and use specialized hardware basically to make that stuff go very, very fast. Okay. So that's not a focus of this particular class, but it is worth pointing out that there are opportunities there, especially with some specialized hardware and some clever matrix and vector math. Okay, so kind of fun stuff if you like that kind of thing. But what we are going to do for this class and for many of the algorithms implementations that are out there, it turns out that adjacency lists are a very good solution. And we are going to lean on our recent experience in homework five with our symbol tables. And in fact, this is going to look a lot like your symbol table. So vertex position 0 is really just a pointer to a linked list, kind of like buckets in our symbol table. And the 9 and the 13 are adjacencies in the graph. So let's look at 0 down here, and we should see that we have a 9 and a 13. So I can very quickly go to position 0. Notice there's no vertex representation for vertex 0. The position in the array gives us a pointer to the adjacencies. And there is no node for 0 right there. It's implied, like we're at position 0 in the array. Therefore, the linked list tells us who our neighbors are. Okay. So as we go down, we'll see, yes, there is some duplication, right? But every vertex gets its own linked list. And every vertex is really just a pointer, a head pointer to a linked list that represents those adjacencies. So if 0 is connected to 9, that must mean that 9 is somehow connected to 0. Okay. So we can see that an edge is represented by one adjacency, two adjacencies in our graph. Okay. So that's a really important insight for a undirected graph. It seems weird, but an undirected graph has two adjacencies for every edge. Because that means I can go from 9 to 0 or from 0 to 9. So if I say, hey, go to 9 and travel to visit all of its neighbors, well, you'll go down the linked list, and for each one of these, you'll jump to that array position and find its neighbors. Okay. So for our lab today, and this is a lab hint, if I say, who are the friends of 8? Okay, well, these are my friends, right? If I'm 8, these are my friends. But who are my friends of friends? So friends of friends means I got to go to 7 and list these folks. And then I got to come back and go to 9 and list these folks. And then I got to come to 13 and list these folks. So those are my friends of friends. These are not my friends of friends, right? My friends of friends are out here, right? And out here and out here. So your lab today is kind of a two-step dance. Go down the list to the linked list, follow those by jumping to the other positions in the array and getting that list, right? So it's sort of like two steps, right? So we'll dig into that code here as we get to the end. But this is the structure we want to get familiar with because it's going to allow us to solve all of those cool problems we were talking about, okay? This is our fundamental data structure that will sit underneath our abstract data type, okay? And one of the reasons we choose this particular representation is because it turns out that most of the graphs that we're interested in are sparse connectivity, relatively speaking. Lots of nodes, not a ton of edges, or not nearly as many edges as vertices. So if every edge, every vertex was connected to every other vertex, it would be an n squared connectivity. So n vertices connected to every other vertex, that's n squared. So that's a lot of edges. This is not a good idea for an n squared kind of scenario. But fortunately, most graphs are not connected that way. Most graphs are sparsely connected. And so this data structure is a really good data structure for us. Okay? So we'll stick with that for most of our problems. Okay? And there's our 6 and our 7, etc. All right, so I think I probably hit on these things. Linked lists is going to be something familiar to us, and it's going to allow us to do a linear search through all of the friends, direct friends or neighbors, and it's going to work well for our sparse graph. We could have a binary search tree there for ordered things, like if we cared about finding our friends in alphabetical order, we could put a binary search tree there, but we're not really interested in that right now. We could even put a symbol table there so we could just jump in and try to find a particular vertex by an ID number. And we could even use an array, right? We're going to go with a linked list for now. It's going to be fine for what we want to do. And we can solve all of our problems relatively efficiently that way, okay? So if I have nodes with lots and lots and lots of children, right, we could do this with pointers. So instead of what we're going to do, we could have done this. Okay, we're not going to do this, but just in case you're curious, I could create a node with an ID value and a dynamic array of pointers to children. Okay, so instead of just having two children like a binary search tree, I could have a variable number of children. And I would have to sort of create that array for every node and then connect it up via pointers. Okay. And we'd have to do that with a little bit more code than you see here. So it's not necessary, as it turns out, if we agree to represent our vertices with integer values, because those integer values act as pointers into our adjacency array. So it's good for us as coders, sort of reduces some of our brain stress, and it simplifies our code a little bit too. Okay? And it's actually faster and more memory efficient. So it's not always the case that we need to use a ton of pointers for this stuff. Okay. So we could do it this way, but we're not going to do it that way. Okay. So just a lot more pointer stuff. So let's get into our implementation of what we are going to do. We're going to have a relatively simple node. It's going to be just like our symbol table. It's going to have a next pointer. So it's not even going to be a double pointer. It's just going to have a node ID that represents the vertex ID and a connector. Okay. So those are our nodes. Okay. Now remember, if I create a head that is a node star type, that's a pointer. Okay. So that is kind of me creating a variable. If I say, hey, that head equals a new node, then we've all done this, I think now. We now have an address stored in the head variable pointing to a node with some ID in there. Okay. So that's kind of stuff we have seen. This is probably one that some of us are still getting used to. So if I say, okay, now I need an array of pointers. So PTR array is a node double star. What does that mean? Well, first off, it's just an address, okay? But it's an address of an address. In other words, it's a pointer to a pointer. So if I say it's going to be a double star, then that means I'm ready to hook up an array itself, which supports pointers. Okay. So this is an array of 4, not nodes, but 4 node stars. Okay. So what am I going to do with that? Well, one thing I could do is say, oh, okay, position 0 of my pointer array is going to be hooked up to that node right there. Okay. So PTR array is a pointer to a pointer, right? And I could do this, right? I could say PTR array 2 gets the address of some new node 6. Okay. So this is just sort of, on the side from our adjacency list, but you can see where I'm going with this. I'm going to dynamically allocate an array of pointers that is going to represent all of the possible vertices in my graph. And then over time, I will hook up little nodes to them that represent their neighbors. Okay. So this idea of the head here will go away. We won't have a head here. This will be the adjacency. And each one of these is going to be a head of some linked list, just like in your symbol tables for your open addressing situation, okay, that you did in your last homework. Okay. So hopefully we're reinforcing that. But that's a double pointer. Sometimes that throws people, and we'll give you some time to adjust that. But think of it this way. It's a pointer to a pointer, right? So there's a pointer in that 0 position, and that's why it's a double star, okay? And that allows C++ to keep track of that stuff. And then we can, of course, follow that to get to the value that's in the node, okay? And we'll be doing that for sure. Okay? Questions on the syntax on that? Okay, all right. Let that soak in a little bit. We'll see more of that over time. Okay, here's our graph class. Now, I'm not going to put it all up there at the same time. And the good news is this code is all pretty much written for you. We're going to work on 2 practice problems here with the time we have left. We'll plow through them pretty quick. But the rest of the code is written. But we need to all get used to what our data members are in our class. So this is the head, not really the head, but it's the pointer to our array that we're going to dynamically allocate, just like we saw on the previous slide. It's going to be the adjacency list for all vertices, okay? How many vertices? This many vertices, right? And then separately, we'll keep track of how many edges, because it's just kind of interesting to know how many edges we have in our graph at any time. Here's our constructor. Somebody says, hey, I need a graph with n vertices. We're going to create an array of pointers to n vertices. Now, none of those array pointers are initialized yet. We should assume they're not, but we're going to come back and initialize them. And then we'll just keep count of how many things we got. So P vertex count is our n, right? So I'm just storing those values here and here, okay? So this is updating that, and this is updating that. No matter whatever you do, please don't do this. Don't say int p count, p vertex count equals n, because that then masks over that and creates a local variable inside of your constructor that will then go away. Okay, so don't put that int on there. That's one heads up, because that does tend to happen. But that's the kind of top level view of our graph class, so, and our simple constructor. Okay. And once we build everything, so this is what we initially kind of have. We have this array that goes from 0 to less than n, and each of those pointers should ideally be null, right? I haven't gone to the trouble of initializing them there, but we should go through and make sure they're null so we don't actually follow them anywhere if they're null, okay? So that's how we're starting out our graph. Now here's the full view. So let's zoom back a little bit. There's our constructor. Somebody could give us the n and an array of edge data, p pairs of integers, and we can build our full graph from just an array of integers, of edge lists, okay? So notice that what I'm doing here is I'm looping through and calling something called an add edge method. Okay, we haven't seen that add edge method yet. Okay, and you don't have to worry about it too much. We'll look at it, but that's how we build that graph from some outside data. Okay, and we're going to have all of these different methods. Okay, and all of these pretty much are going to be given to you. We are going to right now go through and look at this one and this one. Print adjacencies and add adjacency. Okay. But once we kind of build a whole graph, everything is hooked off of this thing here. So our ADJ, probably my arrow should be pointing that way. ADJ is pointing to this array, which has a 0 position, a 1, a 2, a 3, and a group of linked lists that represent the adjacencies for vertex 0, the adjacency for vertex 1, etc. Okay. Okay. Questions before we dive into the code? All right. So graph construction. So let's just look at main to get things started. Because if we've designed our structures nicely, main should not be really messy. And that's going to be really true. Here's some edges. 3 connects to 0, 0 connects to 1. So these are pair Y edges, right? And we could enter these at the keyboard, or we could just create a little data array. P is 4, so 4 pairs of edges. And here's me calling my second constructor. Okay, so NP and my edge array. And now I have graph 1. And hopefully that's all nicely constructed. Here's graph 2. Graph 2 has 101 vertices, but none of them are connected. So that's us calling the first constructor. Okay. And we could do something like this. G2 arrow, add edge 0 to 13. Please connect vertex 0 to vertex 13 in this graph right here. Okay. That's the kind of code we want to be able to express at a high level in our main section. Okay. So we'll be doing that in homework 6. We'll be doing some practice problems. Our constructor 2, I'm not going to dig through this too much, but here's our first constructor, right? That's all we're really doing in our first constructor, right? We're doing our dynamic allocation and grabbing onto n. Constructor 2 is going to do something similar, but then it's going to loop through and call add edge a whole bunch of times. So we're just kind of zooming up on what that thing is doing. Okay, so every edge that we add in this undirected graph will add 2 adjacencies. That's a really crucial thing, right? 2 adjacencies per edge. Okay. And each one of these positions in our ADJ array is the head of its own linked list, just like our symbol table, okay? So a lot of similarity there, which is hopefully helpful, okay? So if you want to know something about vertex 0, we go to position 0 and follow its linked list of neighbors to figure out what those neighbors are. Our add edge function is essentially adding the adjacency from A to B and the adjacency from B to A. Okay, so it's going to this position in the array and creating a node for VB. And then it's going to this position in the array and creating a node for VA, whatever that integer value is. So that's really all we're doing when we actually do that. And then we increment our edge count, right? Because we just added 1 edge, 2 adjacencies. Okay. And remember, we're currently in an undirected graph, so we need both of those adjacencies. Okay, so digging down into that one, what's going on there? We create the VB, right? That's a pointer. We say, okay, if the head is null for that particular VA, just hook it up, right? Just like pushing in at the top of a stack. So that's some really easy code there, okay? If adjacency at position 0 equaled null, then we don't have any neighbors yet. So let's just hook it up, right? Now we don't want to have multiple adjacencies to the same VB. So if it's not null, we got to do like you're doing in your symbol table right now and search the whole linked list to make sure there's not a VB there already. Okay. So the else here means we got to have a while loop. Okay. So let's just look at that high level here. So otherwise, right, we have to say, okay, grab onto the head while the head is not null, search, right? If we reach the end and we haven't found VB, then go ahead and create a new VB and connect it to the end, right? Because we didn't find it in there, okay? Otherwise, we just advance the pointer and keep going, right? So we're going down the linked list and looking for that thing, okay? If we get past here, there was a problem. We ran into a VB, and we don't want to actually put two VBs in there. We don't want to have two friends called VB. So we just flag an error and print that message and say, I can't create a duplicate. I'm not going to do it, right? Okay, so we typically won't run into that unless we have bad data. Okay. Now, this is probably the only practice problem we'll get to do today. So, but I want to make sure that we kind of take it one step at a time. So if I wanted to print out a description of this graph, it's going to have 7 vertices, right? 0 through 6. And there's going to be 7 edges in there that are bidirectional, okay? 0 to 1, 0 to 1, 3, 1, 2. So the colors here are just, so things don't all run together, okay? All right. So the adjacencies are going to be like this. 0 is connected to 1, 2. 1 is connected to 3 and 0. Or sorry, 1 is connected to 0 and 2 and 3. Somehow 3 is missing from that. Sorry about that. Okay, 2, 0, 1, 4, etc. Okay, so apologies, my numbers are a little off there. This seems to be a little suspect. I should have a 0, a 2, and a 3 there. So I think I need a 3 there. So I'll come back and check that. But this is obviously our data structure. We're going to reconstruct that thing into our adjacency list. Okay, so let's go in and look at the code for doing this. Okay, and think about, are we storing edges in this representation or are we storing adjacencies? Okay, we're kind of storing both, but we're going to really call it an adjacency data structure. Okay, and we're going to try not to allow us to have the same pair of edges except going in 2 directions. That's all we're going to really do, like in each direction. And we do not necessarily have a node for every vertex. So let's think about that one for a second. The array is the node, unless there are neighbors or friends for that node. So if I don't have anything connected to node number 17, then there is no node for 17. There's just position 17 in the adjacency array. Okay, so there isn't necessarily a node unless the node is connected. Okay, so let's take a look at the code, see if we can kind of get you to the lab here without too much indirection. Be careful here so I don't lose my video. Okay, let me hide this. Okay, get you dark mode and scale up a little. Now you can search for to do, which will help you a little bit. Okay, but let's just you should notice there's a node here, right? Then there's our graph class, our adjacency pointer, all that stuff we talked about, our 2 constructors, etc. So we are inside of the graph, and hopefully everybody knows you can close up that whole class and open it back up again if you want to skip past it. So those are nice little tools that most editors have. But there's our constructor. There's a lot of emergency data in there, or emergency graph stuff in there. Here's our add edge, right? We're checking to make sure you're not giving me a VA that equals a VB and so on. But there's our adjacencies. We saw this code, right? Here's the code for adding the adjacency. We looked at that little emergency code there. And then there's us creating the node. So we've kind of seen this. It's all written. Here's the searching, right? Next, temp equals next. Here's our get adjacencies. We'll skip over that. Let's jump down to our print method, okay? So how am I going to print the adjacencies? Well, I'm going to loop from I equals 0 to n. but we have a method called vertex count, which tells us what n is. Okay, so we could put p count there or p vertex count, but I'm just going to call the method directly. And I'm going to grab the head pointer. Okay, so notice here, I'm saying get a temp pointer to the head of the adjacency list for vertex I. So what is that represented by? 80j square bracket I. That's the head pointer. Okay. So now I've got the head of the linked list, just like our homework 5. And I'm going to say, wow, temp is not equal to null pointer. Okay. Follow the linked list. Okay. Print the ID of the current adjacency, right? So I'm going down the adjacency for I, and the ID is going to be at temp arrow ID. Okay. So temp arrow ID. Okay, so that's the first adjacency, and then I got to move the pointer. Temp equals temp next. Okay, temp next. So I move my pointer forward. Okay, and the process goes on. And when I get to the very end after the while loop, I just move to the next line, and then we go to the next value of I. Right, that's our print adjacency list. So let's see if I got it right. Okay, very good. So it's saying, hey, how many nodes do you want to create? So let's just keep it simple. We'll say 4 nodes, okay? Okay, and it's saying enter 2 vertex IDs, and they have to be from 0 to 3, okay? Those are our array positions. So I'm going to connect 0 with 1, okay? And then hit enter, okay? And here's our printout, right? 0 is connected to 1, and 1 is now connected to 0. Okay, so that's coming from that method that we just did. Okay, and we can just continue that. Now I can say, okay, now I want 1 connected to 2. And now we can see that 1 is connected to 0 and 1 is connected to 2. So this is my linked list, and this is the position in the adjacency array. Okay, and we can just continue and continue and continue. Okay? So just looking down to main real quick, so we don't, forget the big picture. We're just creating we're creating a graph, okay? And then we're getting 2 values from the user. We're adding an edge for those 2 values, which in addition, we'll call add adjacency twice, right? And then we call our print adjacency method on G, okay? So here's our print adjacency code here, right? You can kind of see all that on the screen a little more clearly. And there's no edges really, right? It's just the adjacencies, but we're representing them by 2 adjacencies. Okay. Okay. And not every vertex, right? Not every vertex has an adjacency. So if I go to output, see, there's no node in there for 3. There isn't, because nobody's connected to a 3. So there's no 3s over here. Okay. So hopefully that helps. Okay. So you can, build these things in any order you want, but notice that if I say I want 4 and then I connect 0 to 1, 1 to 2, 2 to 3, 3 to 0, this is the graph that I'm going to get. Okay. Whoops. But you can build these graphs in different orders. You could say, give me 4 and then give me 2, 3, 1, 2, 0, 1. And you're going to get a different adjacency list over here. Depending on the order in which you ask for these edges. This is the tricky thing about comparing graphs. You can have different orders, like the 3 could be here and the 1 could be here, and it still represents the same graph. So it can sometimes be hard to tell if 2 graphs are the same by comparing their adjacency lists. So there is an algorithm for figuring that out, right? And it's not as exactly straightforward as you might think, okay? But just do keep that in mind. Okay, so adding adjacencies, right? So just a reminder, if I have adjacency 2 here, it's a pointer to node 1, right? And I want to add an adjacency to that. if I say add ADJ to 11, I am adding the 11 here, and I'm now adding a 2 over there. Okay, so that is what it means to add an edge from 2 to 11, okay? So I don't think I have a line. There we go. That's the edge that I'm effectively adding by adding those two adjacencies, okay? Okay, so I think, and we can go on, right? We can add more adjacencies, right? So what if someone says, hey, add adjacency 013? Well, we can't just put an extra 13 in there. Just like your symbol table, we got to search. If we find a duplicate, we need to ignore that request. It's not like it's going to crash our program, but we don't want to create duplicates of our adjacencies, okay? It's already there. We don't need to add another one in this particular graph implementation, okay? So we'll leave that out. No action taken, okay? Same over here, right? Try to add a 7. Oh, here, we'll add a 7. Okay, 13 isn't attached to 7. We found that it wasn't, so we got to plug it in at the end, just like your symbol table, okay? So a little bit of tricky stuff to connect that thing at the end, but once you got it, you got it. Okay, and then the opposite of that, right? We got to add 13 as well. So I think that's all of that, okay? So there may be another interesting one here. Let's just see, adding an edge. So if I say add edge 510, all we're really doing is saying add the 10, right? Add the 5, and everybody's happy. So that's how we'll keep our graph connected. And this is why we say it's undirected, because you can travel in either direction from 5 to 10 or 10 to 5 by following the adjacencies. Okay. There's our edge. Now, we're not going to make you do this, but this is all there is to the code, right? Add edge calls the add adjacency VA VB, VB VA, and increment the edge count. I think we saw that already here on our slides. Okay. So that's all we're really doing for add edge. Okay, both directions. Now, that's our next practice problem, and we're going to save that for next time and try to sneak it in our next lecture, because I want to quick summarize our lab so you guys can get on with your homework or your lab or both. But this little practice problem, if you want to do it, is just about finishing that piece of code. It's a relatively straightforward piece of code, so I will not kind of spend too much time on it next time. But feel free if you want to jump into that. The solution is here, obviously, but we're going to just jump over that, let you think about that. And you should see a lot of familiarity with that code and your symbol table homework, okay? So there's some good clues in there. Also, if you're just finishing out your homework for tonight, okay? But I'll give you that to look at, okay? So let me get on to our lab today. I'll just kind of skip over graph performance for now. But when we think about these different potential ways of representing the graph, the matrix or the adjacency list that we're doing, the memory that we use can be kind of expressed based on the number of edges and or the number of vertices. So that square matrix was like the number of vertices times the number of vertices. So we say that's a V by V space requirement. Our adjacency list is the number of vertices plus a number of adjacencies. That's essentially going to end up being an E plus V. So we'll come back to these other things just, for sake of time. But this is kind of how we're going to start talking about cost in terms of E and V. And is it a cost that's constant, or is it scaled by the degree of V or by the number of edges, etc.? Okay? So we'll come back to this another time for sake of time, so you don't, so you can get onto your lab. So let's talk about lab 21. Not hard. You're going to write a new method inside of the graph class called print friends of friends, and you're going to call it from the main section of your code. So if I am VID, you don't just want to print out my adjacencies. You want to follow each one of my adjacencies and print out its adjacencies. That's what friends of friends means in this new graph data structure that we're using. Okay, so don't even print out my friends, just print out the friends of my friends. Okay, so you'll want to actually kind of write a loop to go through all of my friends, and from that loop, call to get, jump in and print out. You don't even need to call another method. You can just print out the adjacency list of the things that are connected to me. Okay. So here's an example of that, right? So friends of n, right? And we're using letters here, but here's my whole kind of graph using letters. So friends of n, right, would be here, right? But friends of friends, friends of friends are going to be the friends of G, right, which is this, friends of H, right? So you're going to need a loop that's going to go down my friends. And within that loop, you're going to have another loop, right? That's going to go down all of these individual ones. Okay. So somewhere Z is in here. Here's Z, right? And then the A. Okay. That's what we need to do to print out that list. Okay. All right, and I'll leave you with that. Let you guys work on your homework. And again, don't forget about the new, for folks who missed this at the beginning, I've given you 3 slip days. I'm going to call them slip days so we don't confuse them with late days. Slip days are free days. You get to use 3 between now and the end of the semester. So you can apply them to this homework or future homeworks or split them up however you like. Okay, so hopefully that helps everybody. And otherwise, I'll see you on Thursday. All right. Thanks, everybody.